So we are going to continue the discussion on the path integral formulation. In the previous period, we have started constructing. Actually, I have to write it in full notation. Eventually, for the simplicity of the notation, I will consider only the one-dimensional case, one space dimension, not to carry over the arrows or extra indices, space indices. That's the only concern that we have in doing so. If we remember the definition of the K as the xt and x0 t0 in the Heisenberg picture, that was really the overlap between different eigenvectors of the Heisenberg position operator, and there's an overlap. Obviously, it is not as trivial as have being a delta function overlap as in the Schrödinger case. When we particularly clear when we write it in the form of going back to the Schrödinger picture and inserting here the time evolution operator h t t0 x0, and okay, what we do becomes really clear. In a sense, this transition time evolution operator carries this over to a future place, and then you take the projection of this. It is indeed a transition between x0, x points. Each of them are respectively taken at t0 and t times. So in order to go ahead and construct this directly, we have subdivided the time interval into n equal segments. We have to be careful about the numbering of the subdivisions. We denoted them as T1, T2, T3, etc. And there are n minus 1 subdividers because the initial and final points are fixed. These are fixed things, and subdivider are T1 to Tn minus 1. There are n minus 1 of them, and there are n intervals instead. Okay, let's make a note of it. We have seen this in the morning. N intervals and n minus 1 subdividers. Then we do the following. As the Heisenberg position eigenvectors in the Heisenberg picture are also complete and orthonormal, as we have demonstrated before, then we can use that completeness identities and insert them at each subdivider. We insert this one at the T1, x1 point, and similarly at x2 point, x3 point, and at these generic interval, which I will, for generality, we have discussed this in the morning, but we'll continue now more. And then we insert these identities. Identities each involve one integral, right? So how many? The number of integrals is equal to the number of subdividers, which are n minus 1. So we have n minus 1 integrals. The x1 to the xn minus 1. And apart from that, what do we have? This is contracted with the original x0. The x1 is contracted with the x0, t0 in the left. And similarly, this is xn. The end point is our final fixed point. There is x. T is contracted with the xn minus 1, tn minus 1. So how many altogether, how many such combinations? The integral is n minus 1. And there are, let me write it. I will try to use a shorthand. Hopefully I can manage to have a shorthand. Xt, that is the nth point. and xn minus 1, tn minus 1. Of course, there are here a bunch of integrals. dx1 to dxn. Let's save some space by saying that there are that many integrals like that. Going all the way to x k t k x k minus 1 t k minus 1, and going all the way to x1 t1 x0 t0. Okay. Each interval now of infinitesimal length, which is defined as epsilon is t minus t0 divided by n intervals, and their lengths are epsilon. And each of these factors there are these infinitesimal transitions, okay? That is the transition between that and that point, this and that point. So what is the idea? The presence of integrals, of course, it has a beautiful further elaboration later. What we can think of is either a single shot transition, or we can think of doing a single shot transition in sequential steps, in n steps. That's the thing. That's the first step, and then the second step, and that's the third step all the way. That's the kth step, right? That was the first. That's the kth step. And that's the nth step. And integrals are here. I will elaborate on the integrals, but then we have what we have done in the morning. We have considered this generic transition amplitude, which we have denoted as symbolically, it is the transition in the kth step. Explicitly, it is this thing, k1 minus 1 to k. I'm not going to put in the arguments, it is that particular expression. And we have shown that it is equal to, it can be represented as 2 pi h bar e to the I over h bar pk xk minus 1 epsilon. This I denote as, to emphasize that it's a C number Hamiltonian function of all those entries, pk xk. So that's very nice, really, that we have such an expression. Then what we have to do is put all these together in that expression. So in addition to n of those integrals, actually n minus 1 of those integrals, correct? Because they are at each Then, how many pk integrals? Pk counts the number of transitions. Zeroth to 1, the first, n minus 1 to nth. So there are n of these integrals. Because p counts the intervals, x counts the subdividers. T and x, they are subdividers. P is connecting the endpoints, so they are counting the number of intervals. So I can write this as, let me use a clean notation, because from this point on it may get really cumbersome. Not to make it look cumbersome, I have to use clean notation for this. All right. This is the x integrals. As you notice, there are m minus 1 of them, and there are p integrals, but it has this factor underneath, dp1 to th1. Then we have to collect the exponentials together. What are the exponentials? Exponentials are those expressions. Times. Let me write this separately just to make them visible. What is that exponential factor now appearing in here? You have to put all these things in, right? For each factor. For all these factors in here and many factors, there's a representation of this sort. So what is it? It is e to the I over h bar epsilon k from 1 to n epsilon pk xk minus 1 divided by epsilon. I will explain. Don't worry, it looks a little cumbersome, I know. Minus h pk xk. Let's try to digest now. What did I do? For each of these factors, which are n many, I have that thing for each of them. I put the integrals in a group of p integrals with the correct measures 2 pi h bars. X were already there due to the original insertion of the completeness identity. And I have put these together. That is, for each factor, there's an exponential factor like that. We add, using, these are C numbers, not operators, e to the a times e to the b times e to the c is equal to e to the a plus b plus c. That is what I'm doing. I'm summing them. So how do I collect the epsilons in here? There are this many summations because coming from each factor, and I add the exponents. I take this epsilon out. Notice that that's what I have done. Epsilon is the length of the time interval. I take it out like that by putting an epsilon in here. This is going to enable me to get the x dot, right? Remember, from the configuration space to phase space, when you make a transformation, it is p times q dot minus the Hamiltonian gives you the Lagrangian. So you're feeling how it moves towards bringing the Lagrangian in. So that's the reason why I factored the epsilon and left the h without the epsilon and put the epsilon down in here, p times xk minus 1 divided by h, epsilon. Counting is important here because there are n of those integrals, so there must be n of those factors. Despite the fact that the number of x integrals is 1 less. That's such an important asymmetry. Aesthetically, at first, when you are doing it for the first time, you may think that, am I doing something wrong? The symmetry between x and p in the phase space. Phase space is composed of x and p coordinates together, right? If it is one degree of freedom, it's easy, x and p. But here, when the number of degrees are increasing, there is a sort of a mismatch in the number of xp integrals. Would that be a problem? Or would that be something which is going to really crucial for the success of the formalism? The answer is the second, of course, here. Now, but let's still proceed. Let's see what I can make out of this. Now, what do we do at the end of the day? This is the construction for this discretized subdivisions in finite numbers. But the basic principle of calculus is that at the end of the day, you have to let the number n goes to zero, infinity, or equivalently, you have to let the length of the infinitesimal subintervals to zero. Right? That's the basic principle. If we do that, what do we get? That's what we have to do in order to get a sensible result. And okay, I would like to get rid of this region. Paying attention to this one. There are n many things, an epsilon and this argument. You are building on those arguments on epsilons. That's the area, right? The integral under, and the integrand is this expression. What is this expression then? Let me write it separately. Exponential. Let me handle this separately because it's a crowded expression. What happens to the exponential when epsilon goes to zero or n goes to infinity? It goes to the following expression, correct? dt, t0 to t, let's use a generic integration variable dt prime, times p x dot minus h p and x. Is that really what it is? Notice that if you look at that generic interval, xk minus 1 divided by epsilon, when epsilon goes to 0, that goes to time derivative, right? That's the derivative of x. Starting from here, x plus epsilon minus x divided by the length of the interval. It is nothing but the time derivative of x. This is the representation of time derivative of x. The first one is p, and minus hpx. The measure is really strange, and it should be denoted accordingly. What about the measure? Integral measure, of course. The measure was the product of all these that goes in number to infinity in principle. So we will denote this measure now. When epsilon goes to 0 or number n going to infinity, it is what it is. In principle, to start with, the measure is like this. dxi, I is from 1 to n minus 1. That is what it stands in there. We will denote this using Feynman's notation. That's dx. That's a new measure. The definition is this. When you unfold to carry out the expressions, the measure is to be unfolded like this. So when n goes to infinity, we will denote it as such. That's the Feynman's measure. That's the one part. The other part is the integral is I, or if you want j, from 1 to n dpj divided by 2 pi h bar, and when you let n goes to infinity or epsilon goes to 0, you will denote it as dp divided by 2 pi h bar. So that new notation of measure is obviously makes it different than the ordinary integral measures of Lebesgue or Riemann. This is the Feynman's measure, and when you write it symbolically as such, When you unfold to go to the discretized space and time, these are the explicit expressions associated with them. Notice the mismatch in numbers. Therefore, at the end of the day, I write the Feynman transition amplitude of xt and x0, t0. Of course, when you put the times explicitly as a label, this is the Heisenberg picture transition amplitude, it becomes, that's final results. dx dp divided by 2 pi h bar. That's symbolic way of writing. So it doesn't mean that single 2 pi h bar. So that's misleading. That's the reason why I erase it. That's the meaning explicitly. Another equivalent way, some people prefer to use another equivalent notation for measure. They write it as with a curly bracket, 2 pi h bar. That's also meaning, Feynman measure. Notice that if there is no bracket or funny notation, it is the ordinary integral measures. This or that is a way of representing Feynman measures, and this one also sometimes represented as dx. Putting the bracket around here explains what you are talking about. Different measure, and when you would like to unfold this, that is the way you unfold it. And similarly here. So I will drop this 2 pi h bar and will remember when I'm unfolding, opening up, that it must be there. So to make it a clean notation now, that's the dp times e to the I over h bar t0 time integral is t0 to t dt prime x dot p minus h xp is the answer. Looks very simple, isn't it? But of course, the simplicity of the notation shouldn't mislead you. It is horrendous. There's so much behind each notation. That is that. So x dot means then dx dt prime. Because it is the generic t integral variable I am using, and I am integrating it from t0 to t. That's it. That's the result we have, and if we are going to use this in the quantum field theory, in the continuous infinite degrees of freedom, we are going to generalize this expression. That's a good starting point. However, for a class like this, quantum mechanics, it would be nice if we could reduce this to the Feynman's form, which we took as our starting point early this morning. Particularly Feynman's, at what point Feynman's was inspired, and how did he really proceed, went ahead to construct such a method. In order to see this, I have to now focus on, so this is the general form. It is written in the phase space, and despite the fact that there's a mismatch in the number of integrals when you unfold them, but it involves x and p, depending on the number of degrees of freedom. It's a phase space integral. Therefore, for example, some of you may say, when we go to the relativity, would there be any problem with the covariance in the Einstein's sense of relativity? You may or you may not, but in order to answer all those questions in a more proper way, we have to proceed in reducing this to Feynman's form. So this step is reduction to the Feynman's form. This is a very formal construction. Notice that it was just based, this entire construction was based on the meaning of the k being the transition amplitude between x0, t0, and x and t. or it is the matrix element of the time evolution operator, e to the minus I over h bar h times t minus t0 between position eigenvector bases of the Schrödinger picture. So that's the mathematical, that's what I have done. This is what that expression is. And how is it related to Feynman's form so that you can really think of, go back to all those nice physical interpretations? We have to restrict our attention to, let me again stick to one dimension, x and p, because adding extra dimensions doesn't do any harm apart from introducing new indices. New indices are bad, you know, because there is x, one-dimensional x, and the values xk or xk minus 1 are its values on the time lattice. If I introduce this other coordinates, like either I have to introduce x, y, z, or x1, x2, x3, then I have to put additional indices to indicate that there are other space indices. But so I don't want to complicate the picture. I will stick to one dimension. The result is as general as possible, apart from that suppression of additional indices. This is not special. This is not a special case. It is the most general case. So how do we proceed? When the form of the h is p squared over 2m plus v of x. What do I mean? I say that if all the forces are generated by the local potentials, which are functions of x, or in the absence of velocity-dependent potentials. This discussion leaves out the electromagnetism, but introducing it easy via the covariant derivative method. So this doesn't mean that we are doing something special. This is as general as possible. Proviso that when we include electromagnetism, we are going to do the proper modifications. Just to set the stage and to understand the notation in this simple case. Consider a case of that form, kinetic energy plus potential energy. These are you may say, of course, these are the most general forms. A class which contains almost everything except the gauge theories, but leaving gauge theories out is not a good thing. We are going to introduce them later. How does this expression reduce for the special class of Hamiltonians of that form? What we have to do is go back and undo. Go back to K. That form of K. And undo everything. Which part of it is relevant for my present discussion? It is the P integration part is relevant, because notice that in the H there is this, and also in the Legendre transform part there is a P. This doesn't depend on P, so it can be moved to the X integration part. I have to take this and that part in and focus on this. Okay, let me focus on that part. So what I have is I 1 to n dpi divided by 2 pi h. That's the integral part of it. There are that many integrals and with those measures. Times e to the I over h bar epsilon. I'm unfolding everything. That, and I put that together. So xk, pk xk minus 1 divided by epsilon, correct? That's what I have, minus pk squared divided by 2m. Let's first of all convince ourselves that the p-dependent parts can be represented as such. This is the integral here. In the measure, I had n many dp divided by 2 pi h bar, and in the exponent, when you write it in the conventional infinitesimal calculus form, there are also n many of these factors. Remember here? Therefore, this way of writing is a good way of writing. Because this product, this is product, right? dp1 divided by 2 pi h bar, dp2 divided by 2 pi h bar. There are n of them, capital N of them, and each of them carries this. So it is easy to write this as dp divided by 2 pi h bar, dp divided 2 pi h bar, and combine all these. This is symbolic, you know it is k1 to n. This way of writing is the same as that way of writing. This product takes care of this exponential. Now I'm free to focus on a single thing. So if I can carry out that p integration and get rid of it, can I? It looks horrendous, but it's not really. It's very innocent, apart from the indices. This is how you should think of it. So it is not a very technically relevant part. So let me do it here. Okay. So can I finish with that? If I finish with this single, sorry, perhaps I have the labels I and I, they should be, let me retain K. K is a good notation, it's visible. Let me convert them to K. So that this is equivalent to that one. For each K, I have dp divided by 2 pi h bar, one exponential. Put n of them together, and you get the lower part and that part. So let me do each integral, this integral, dpk divided by 2 pi h bar, exponential I h bar, epsilon. I will take this minus 1 over 2m out. What is left over? There is pk squared times 2m divided by epsilon, 2m divided by epsilon, moving this thing up, xk minus 1, p, k. I have rewritten it by moving this minus 1 over 2m to the left, leaving it in such a form which can be completed to a full square. How do I complete it to a full square? I can write it as pk minus m over epsilon xk minus 1 squared. Is it familiar? Indeed, so it is. There is 2 and pk, and there is this intermediate quantity which I have written in here. pk minus something squared, but that something squared, of course, contains an additional piece, the square of this thing, which I have to subtract from here. M squared divided by epsilon squared, xk minus 1 squared. Nice. Notice that this second term times that additional thing in the front, multiplying this, is independent of the pk integral. I can move it out. It becomes now what? There's a minus 1 over 2m and m squared, so it is I over h bar, 1 over 2 times m, xk minus 1 squared divided by, there is an epsilon in here, 1 over epsilon squared in there. How nice. Again, you recognize this, right? 1/2 times m times velocity squared when you put everything under the integral sign. What is left over inside is dpk divided by 2 pi h bar times e to the minus I epsilon divided by 2mh bar pk minus something squared. I write something because I'm not interested, but I know what it is. That something is that expression. The integral is from minus infinity to plus infinity. Then you can carry out this integration first by shifting the variable pk, write it as qk. pk minus something is I redefine as qk, and that is independent of the pk, so the measures are the same. This becomes dqk. And if I call this alpha now, what is the result of this integral? I can now finish that integral, right? Let's not get confused with the upper line. That's our new line. That belongs to the upper portion. What is this integral now? Let me write it cleanly once so that you can see it. Use a different color. I'm interested now computing this integral. Okay. What is that integral now? dqk 2 pi h bar e to the minus alpha qk squared. That is, I have reduced through these redefinitions, I have reduced that integral to this form. What is it? There is 1 over 2 pi h bar already in here, and this is pi over alpha. Alpha is that coefficient. So let's substitute everything together now. What is it? 1 over 2 pi h bar times pi over alpha. Alpha is I epsilon divided by 2mh bar. Okay. So 1 over 2 pi h bar times 2 pi h bar m divided by I epsilon. Or, you recognize this because in the introduction section we have got an expression of this form. M divided by 2 pi h bar I epsilon. How nice. You see? It is this integral now, this. And the result is this. Fine. Let me go ahead. This was the exponential that we were doing for that case, so I can erase this middle section to finish our computation. You know, when out of that rather complicated looking expressions, we are really getting there. So what is this? This single p integral in here, that one. What is it? Let me carry this over to here. It became the following expression. M divided by 2 pi h bar I epsilon times that expression. E to the I over h bar 1 over 2 m xk minus 1 squared divided by epsilon. That's the result of that. It is the result of this. Okay. So there are how many of them? K from 1 to n. So I have to put this product. K from 1 to n. Because it was under this product. One of them I have done. There is this thing in the front. So what else left over? What has left over was this portion I haven't touched, and x integral, x Feynman integral I haven't touched. So let's put everything together. K contains unfold yet, but let's unfold it. This is fold. So unfolding means I 1 to n minus 1 dxi. That is this portion of the Feynman measure. I have written it like that. And there is this term which is carried over. How many of them? E to the minus I over h bar epsilon sum over k I or I 1 to n. This thing. There is an overall minus sign in the front. That's why I have put that minus sign. Vxi. Okay. And there are those terms. Plus I over h bar in here. I over h bar is out. So there is plus, I have to put them, I put the minus out there. Let me put the minus in. I'm carrying this over inside. 1/2 m xi minus 1 squared divided by epsilon. You may say you are going back and forth from I to k. Yes. I's or k's or j's or n's are labeled, dummy labels. Whatever I need, I insert them in. Okay. So here, as I have labeled them with the I put that in. That is put here correctly, but there is also a measure there. And many of those measures. That comes in here. That's the exponential part. Is there anybody or anyone among you that noticed that I made a small mistake in number, innocent, but actually vital? How many of these factors? N. Right? From each integral, I had n of them. Put that exponential in here, and as the sum goes from 1 to n, it's correct. The norm, if the front factor is there are n many of them, but if I collect this under this measure of x, it is n minus 1. There is one extra. What is that one extra? I have to warn you that when you read books or papers or review papers, they overlook. They make a mistake and they correct it out of hat. They don't know what they are doing, really, mostly. In even all the books. There is this extra factor in here. One factor, m 2 pi h bar I epsilon. It's so important that I have to color it. This is n minus 1 of them, because this runs to the n minus 1 from each, and there is one additional. Seemingly ugly, seemingly destroying the aesthetics, seemingly doing many bad things, but saving the physics and mathematics, really. Okay. So I am more or less there. Let me try to finish with that. Okay. So I'm really done. We will write this now as dx. What is inside? Inside the exponent is, notice that I over h bar epsilon, this is 1 for each factor, right? Actually sorry, I have to do this. Let me leave this out. let me move this, put this in, that's much better. From I to n minus 1 integral, and there is sum over n, yeah, correct. So this becomes I over h bar, line integral dt prime t0 to t, because when you take the integral, you subdivide and put the infinitesimal length, the area of each rectangle, the rectangles, and then you sum, right? dt prime. What is inside? It is really L, right? 1/2 m, the velocity squared minus the v. That's the Lagrangian, isn't it? And what is measure? For each one additional factor more. That is this extra factor in here. N minus 1 of them go together, and there is the additional one, n over 2. So when you are going to do any actual computation, when the v is specified, then you have to unfold and go to the time lattice and put those measures correctly with the correct number of m, these initial factors, and that gives you the k in the Feynman's form. This is the form noticed by Feynman in Dirac's book, but it wasn't really this form. It was directly e to the I over h bar times the classical action. Notice that although the classical action appears in here, there are so many integrals in here. Let me go back to the original construction and try to interpret what does it mean that in presence of those additional integrals in the Feynman measure. What does it mean? Let me give you the answer. It will mean sum over all paths connecting the x0 to x, sum over all the infinitely many paths. They are contributing properly of their shares as compared to the classical mechanics, which only involves a single path, classical path, whose property is that it minimizes the action. That's such a fundamental difference. And although it was sufficient to catch the attention of a great scientist like Feynman, to reach to that result eventually is radically different. It has nothing to do with the classical physics. This classical path which minimizes the action is just one of those infinitely many paths contributing to this action, to this transition amplitude. Eventually, if you let h bar goes to 0 from this exact quantum expression, that you can recover that classical expression. That's another issue that we may or we may not pick up eventually. But it's a good point perhaps to stop at this point. Then after the break, I will comment on that sum over paths first, and then we will try to reproduce the free particle result using this beautiful formalism. You'll see life will be quite tough, but it is worth it, really, because you don't borrow anything from the canonical substituting to get a result. You do it from zero. Till now, we have been constructing everything from scratch, from the very definition and the construction of explicit form of free particle propagator also will be done using the same logic. From scratch we'll construct it. And some of you may say, it's not worth it, it's so difficult, perhaps we should stick to the conventional. Of course, that's a matter of taste. We'll see after the break.